what we'll do, and this, yeah, triple scalar product. Right, so one of the concepts is the magnitude of the cross product. And so that's actually fairly simple. Nice. It's actually fairly simple because it's related to a rule. And we'll talk about the justification of the rule in a few minutes. And we'll do a little proof. And then we'll go from there. So the magnitude of the cross product between two vectors is the dot product of the two, well, if you're multiplying two scalars, you're dotting them anyway. So the magnitude of u times the magnitude of v times the sine of the angle separating those two angles. Now, you may look at this problem and say, well, I don't want to use your fancy formula because I think it would be easier to just find the cross product and then find the magnitude of that result. And I would agree with you, but we need to kind of verify that this rule is going to work. So we're going to actually do it both ways. All right. So first we'll use our rule. All right. So we're going to have the magnitude of u. So we're looking for the magnitude of u cross v. I need the magnitude of u, the magnitude of v, and the sine of the angle between them. All right. So the magnitude of u. It's along the y-axis, so it's a clean 4. I mean, you could do the squared values added together and then take the root, but that's what it's ultimately going to end up being. All right. Then the magnitude of v, by the same rationale, is going to be 3, because it's along the z-axis, 3 units away from the origin. All right. So now we just need the angle between these two vectors. All right. We could solve for it. But if you have a good visual sense of what's going on here, then you should already kind of know what that angle is. But let's say you don't. All right, so cosine theta is equal to uv, the dot product of uv, over the magnitudes multiplied. All right, so I'm not going to really do much work here because the dot product itself is just going to be 0. All right, so as long as the magnitudes themselves aren't 0, then we're good. All right, that's why we say that if the dot product between two vectors is equal to 0, as long as one of those two vectors is not the 0 vector, then you're looking at an orthogonal relationship. All right, so I have cosine of theta is equal to 0. Now I could solve for the angle, but ultimately I want to find what the sine of theta is. All right, so theta would be equal to the inverse cosine of 0, but then I can take the sine of both sides of this equation and just write the sine of theta is equal to the sine of the inverse cosine of 0. All right. That's assuming you want it to be more of a calculator type problem. Right, so if I do that, then I'm just looking at 4 times 3 times the sine of the inverse cosine of 0. And again, something that's very, very calculator ready. All right, so you can look at it and say, well, cosine, where is that going to be equal to 0? That's going to be either at 90 degrees or 270 degrees. Right? Either way, when I take the sine of that value, that angle, I'm either going to get plus or minus 1. Right? So positive or negative 1. Since I'm talking about a magnitude is an absolute value. One way or the other, I'm coming up with a 1. Right? So the calculator may tell you that this result is negative 12, but you would drop the negative anyway. All right, so we're looking at a result of 12. So this magnitude of the cross product is equal to 12. All right. So we're going to want to start thinking about, okay, well, what does that mean? But before we get into that, let's talk about the other approach that you might consider using. Now, the other approach I think is more beneficial when the angle between the two vectors isn't easy to come by. In this case, I've been doing this a while. So I kind of know what to look for. You know, in theory, you're either there or you're getting there. When you look at, you're looking for the angle between two vectors, you look at the two vectors and see if they're going to zero out through the dot product. All right, so looking at the corresponding parts, if you multiply them, will I get 0? If the answer is yes, then you use this approach, all right, uv times the sine of theta. If the answer is no, then you would most likely use the other approach where you find the dot product between those two vectors, all right? So, sorry, cross product between those two vectors. So I'm going to find u cross v. All right, so we know it's going to alternate in sign, I, then negative j, then positive k. So for the I, it's going to be 4 times negative 3, so negative 12. So diagonal down minus diagonal up, so negative 12 minus 0 is just negative 12. So I'll just highlight that part. Now for the j and k, in either case, we're finding the determinant with a column that contains, well, it doesn't have to be both columns, but all it takes is one column containing all zeros. If that's the case, then the determinant for each of those parts is going to be 0. All right, so this boils down very nicely to just a negative 12i, all right, the magnitude of which, you do the work, but it's just going to be equal to 12, all right, so you'd get it that way too. So a little bit simpler, sure, but not always. All right, so I'll put a star on the next one. And then we'll talk about the area of a parallelogram, because that's all going to kind of tie together with the concept of the cross product. All right, so I have a diagram labeled up for you because I guess you got to start somewhere. If we locate vectors u and v such that they form adjacent sides of a parallelogram, then the area of the parallelogram is given by the magnitude of the cross product between u and v. All right, so area of a parallelogram is base times height. So the base of this parallelogram, well, the vector itself doesn't represent a length. The magnitude of that vector does. So the base is the magnitude of u. The height, I labeled it up here, but I do want to take a second and talk about where this is coming from. So I have an angle here, and this unknown side that I'll call h for height, right? Because I'm looking for base times height. All right, so ignoring the v sine theta, because that seemed to come out of thin air, what I'd be looking for is the sine of theta is equal to the opposite side over the hypotenuse. Now the hypotenuse, again, is a vector, but if it's going to be a length, it has to be the magnitude of that vector. So hypotenuse would be the magnitude of v. Now if I solve this for h, I get v, magnitude of v times the sine of theta. All right, so opposite over hypotenuse. All right, so let me turn this off. All right, and so that's where the v sine theta is coming from. Now if you chuck that into the formula for area of a parallelogram, you're looking at magnitude of v times the sine of theta being multiplied against the magnitude of u. So that is designated as the magnitude of the cross product of u and v. All right. So what this tells us is more of an intuitive understanding of what a cross product is really giving us. The length of the cross product between two vectors is equal to, by definition, the area of the parallelogram formed by the two vectors. And that would be the parallelogram that you would create in order to find the vector sum. All right. And so what that's getting at is the idea that it ties together nicely with the concept of area, right? Because determinants and areas represent the same thing. So a determinant of a 2 by 2 square matrix would be the area corresponding with that 2 by 2 square matrix, right? The determinant of a 3 by 3 square matrix would be the volume. So we extend it into the third dimension, the volume of the parallelepiped formed by the three vectors that make up that 3 by 3 square matrix, all right? So what this is telling us is that the cross product is in essence getting at that same idea, but we're not limited to just square matrices, all right? So if I needed to find areas on the plane, a two-dimensional, three-dimensional system, I could use this technique in lieu of the determinant, because if you're going to find a determinant, how are you going to do that if it's not a square matrix? So this technique is the workaround for that. This will be pretty much it. We don't need. So a couple of problems where we apply this concept. I'll do one of them with you, and then I'll start the other one. So it really doesn't matter because they essentially end up being the same thing. So I'll do the second one, so I'll start with the first one. All right, so we have the ordered triples. They're pretty convenient ordered triples, and I'm saying find the area of the triangle. And so you might be saying to yourself, well, wait a minute, you just talked about the area of a parallelogram. How are we supposed to know the area of a triangle? All right. Well, a couple of ways. One would be to just really modify the formula that we use for area of a parallelogram, because area of a parallelogram is base times height. Area of a triangle is base times height over 2. So just take what you would get for a parallelogram and chop it in half. All right? So area of a triangle is 1/2 the area of a parallelogram. The other way is more of a visual approach, but it really amounts to the same thing. It's really just a matter of taking the triangle that you have and replicating it to create a parallelogram, then finding the area of that entire parallelogram, and then chopping the result in half. All right, it amounts to the same thing though. All right, so what I need are some vectors. So I got to decide where I'm going to pin this. I'll pin it at P. So I'm going to get vector P to Q and vector P to R. So negative 1, 1, 0. And negative 1, 0, 1. All right. So I'm looking for an area, so it's a question of do I want to find the cross product or do I want to use the shortcut rule, which, again, doesn't always amount to being a shortcut. It's already in vector form. I can easily find the dot product between these two quantities, so that's what I'm going to do. It doesn't end up being 0, so we got a little bit more work ahead of us, but nothing crazy. So cosine of theta is equal to, again, u dot v over the magnitudes multiplied, but in this case it's pq dotted against pr and those magnitudes multiplied. All right, so the dot product is just a 1. The magnitudes are each radical 2. 1, negative 1 squared plus 1 squared plus 0 squared in both cases. Yeah, square root of 2. But then square root of 2 times square root of 2 is just going to give me a 2. Kind of interesting how this unit circle stuff keeps coming back again and again and again and again. You're supposed to have a quiz tonight, but I forgot to make copies of it, so it's not going to be tonight. So you're off the hook. So, and I have something. I got a full lecture plan for Thursday, so so we'll just do it next Tuesday. And there also is a bonus opportunity coming your way. I set a remind for it. I think it's coming out tomorrow, though. But it's another game, this time with tangents, right? Because that's what the unit circle quiz is. It's the unit circle, and then you also have to state the tangents all the way around the circle. And so that's what the game will do, too. Right? So another bonus opportunity. It's just, again, like I said last time, it's me trying to trick you into studying for the unit circle quiz. All right, so. What's that?
The quiz, it will be the same
as the last one?
Yeah.
No, because it's going to have the tangents around it too, right? So it's kind of a step up. But if you do the bonus that comes out tomorrow, you'll know what the quiz is basically. So cosine of theta is equal to 1/2. So unit circle values, but again, maybe you don't know it, so you write it as theta is equal to the inverse cosine of 1/2. And so the sine of theta is equal to the sine of the inverse cosine of 1/2. All right, we're looking for an angle between these two vectors. It's pretty reasonable to assume that it's going to be an acute angle. So, I mean, just by looking at the picture, you know, you can't always assume it's drawn to scale, but if it were obtuse, it would be pretty obvious, I think. So, you know, you're just looking for the sine value that goes along with the cosine value of 1/2 on the unit circle. And so radical 3/2 is always the companion to 1/2. It's just a question of whether it's positive or negative. So you pretty much have it. It's just a question of whether you want to include it yet or you want to include it in the next step, which is where we take our rule, which is the magnitude of the cross product of u and v, in this case pq and pr, is going to be equal to pq pr. Just, why can't I undo? Oh, that was weird. It just glitched pretty crazily. PR times the sine of theta. so each of my individual magnitudes are radical 2 times the sine of the inverse cosine of 1/2, which you could just chuck in the calculator if you want. But ultimately, when all is said and done, nothing left to say or do. So you'll have radical 2 times radical 2, which is 2, times radical 3 over 2. So it'll all come out to radical 3. Now again, the area of a triangle is going to be half of that. So radical 3 over 2 would be this area of a triangle. All right, and it all comes back to this idea here, that area of a parallelogram is twice that of the area of a triangle. So take the area of a parallelogram, chop it in half, and you have the area of a triangle. All right. But yeah, pop it all in the calculator if you want, but or use the cross product approach and then find its magnitude. But still, you'd have to chop it in half in the end. All right. Page 70. There we go. So area of the parallelogram with vertices, this, that, and the other thing. I need some vectors. So what I'm going to do, now this is in 3 space. So I'm going to just draw a quick sketch, best I can, you know, because it's going to be a disaster for me anyway. It's just a question of how disastrous. We just want to rough it out. It doesn't have to be perfect. You just want to get an idea of the order of things. So 1, 1, 0, 1 in the direction, so I'll label it up X, Y, Z. 1 in the direction of X, 1 in the direction of Y, no change in Z. So we're talking like right about for that point P. All right, the next one is 7, 1, 0, so 2, 3, 4, 5, 6, 7. 1 in the direction of Y and no change in Z. So we're living in the XY plane, that's point Q. Now R and S are going to be elevated, so I have to go out 9 in the direction of X. So let me clean this up a little bit. Four in the direction of Y. And then 2 up. So I just pop it right here. That's going to be R. And then 3, 4, 2, that's going to be about right here. That'll be my S. All right, so now I'm really just doing a rough sketch because I don't really care about where the points are per se. I really care more about just where they are in relation to one another. All right, even if my diagram didn't look much like a parallelogram, I don't even care about that. All right, but if you are wondering, it is a parallelogram with a little bit of height. Right, so it's kind of like, if you're thinking about it like this in the 3-dimensional sense, it's kind of like a little ramp. All right, or piece of paper where one side is on the XY plane and the other side is just kind of floating up in the air. All right, so that's the graph of it, but again, we didn't need a picture perfect graph. I just was wondering what was that, because that's not typical. So P to Q 7 minus 1, 1 minus 1, 0 minus 0. So I'm working off of this guy. I'll create that vector. Now all I need are two consecutive vectors that make up the parallelogram, because after that I'm going to find the magnitude of the cross product. All right, so 6, 0, 0 seems to be one dimension unless I screwed it up. PQ, 7 minus 1, 1 minus 1, 0 minus 0. So that's not bad. I can work with that. And then I'll go P to S. So we're looking at 3 minus 1, 4 minus 1, and 2 minus 1. 2 minus 0. So 2, 3, 2. Right, so we could find the cross product and then find the area, but, I'm sorry, find a cross product and then find the magnitude. But we kind of already did that for another problem, so I might as well take you through the other approach again, which is the finding the angle and then using the shortcut rule. All right, so, which ultimately, again, is not always a shortcut rule, but we'll take it. So in this case, cosine theta, PQ dotted with PS. And I kind of use as a general rule of thumb that if I see a bunch of zeros in one of the vectors, that means the dot product's going to be pretty easy to do. Same thing with the magnitude. So if that's the case, then I might as well just use the angle formula. So cosine theta, your numerator is just a 6. The magnitude of PQ is also a 6. I just need the magnitude of the other one. So magnitude of PS (4 plus 9 plus 4). So we're looking at root 17. All right, so the 6's would cancel, leaving me with a 1. And so I get cosine of theta is equal to 1 over the root of 17. And again, I don't actually have to figure out what the angle is in order to continue with this. So I'm just going to find theta as the inverse cosine of 1 over root 17. All right, because I know that the magnitude of the cross product between PQ and PS, which ultimately is going to give me my area, is going to be PQ magnitude multiplied by PS, also magnitude, multiplied by the sine of the angle in between them. That's what I was looking for. I knew it was something important. So sine of theta. So 6 times root 17 times the sine of the inverse cosine of 1 over root 17. And once we have that, we'll have our area. All right. And for this, it doesn't matter what mode your calculator's in, because even though we're taking the inverse cosine, then, you know, if you're in radian mode, that'll give you a radian measure. If you're in degree mode, that'll give you a degree measure. But once you take the sine of it again, it puts it back as a ratio, so it's all good. So 6 times the square root of 17 times the sine of the inverse cosine of 1 over the square root of 17. Close them up twice. And hope you don't get something nonsensical. 24. Oh, of course it's 24. 24 square units. It kind of makes sense that that it would be a clean answer, because you have a multiplier of rad 17, and the ratio that you'd get for the sine function would have a denominator of the square root of 17 in it somewhere. Or, I'm sorry, it would just have, not necessarily a denominator, it would just have a square root of 17 in it somewhere. So, one way or another, it was going to clean up with that rad 17 on the outside. So, it's kind of nice. Pleasant surprise. Very mathy looking. Yeah. So then we get to the triple scalar product. Very, very intimidating sounding term. Actually, it just sounds like just taking terms from the course and just throwing them together at random. Triple scalar product. Nah, he's just making stuff up now. It's triple because there's three things. It's a scalar product because ultimately, in the end, even though you're going to have vectors to begin with, you're taking a dot product, which is also known as a scalar product, right? So three things multiplying through a dot product. So that's where the name comes from, all right? And the result is always going to be a scalar, right? So triple scalar product of vectors, this one, that one, and the other one, is the determinant of the 3x3 matrix formed by the components of the vectors, right? So I'm going to take you through this. It's not quite a derivation. It's more of kind of a, I'll say a justification. But I do want to show you the connection, right? So let me just have a purpose, right? You know, like, what's the point? Be like, yeah, I got another question right. I don't know why. All right. So, again, I'll pop this in my calculator. I'll get a very, I'm sure, impressive looking answer. Theoretically, we have a little sense of where these values are coming from, which is good. But we also would like to know, okay, that's wonderful. But why? Because there was a person somewhere along the lines that said, you know, it would be really cool. Take the cross product and then on top of that, multiply it by another vector using a dot product. If we do that, that would be really awesome. Like, I'm sure that, like, people would be lining up to date me after that. You know, like, I create that rule, like, they're just going to be beating down the door. Nah, it didn't really play out that way. They were already rich. They're like the people who came up with all these mathematical things that we're required to learn about now. They did so because they were already, like, incredibly wealthy, to the point, like, if you ever thought to yourself, like, whoever came up with this must have had a lot of time on their hands. That's what rich people have, a lot of time on their hands. And so some of them end up doing, like, what ends up putting them in the tabloids, and then some of them create triple scalar products, right? And so, like, they already had everything they wanted, and they're like, you know what? I want to better myself through the study of mathematics. You know, I needed a job, so that's why I do it. Yeah, so determinant. And again, still no idea why. Finding these determinants. Oh, -8. Ooh, fancy. I got my triple scalar product, which is, again, the same as the determinant, which again is a cross product followed by a dot product. All right, so now we got to be thinking about, all right, what does that do? So the cross product gives, well, the magnitude anyway, the magnitude gives you a length that's consistent with the area of a parallelogram. But the cross product itself gives a vector orthogonal to two given vectors. All right, so I'm starting off with my two given vectors. I got one going this way, one going that way. That's my cross product. All right, that's easy enough. Now, we talked about the idea that the magnitude of the cross product is going to basically simulate a parallelogram. So I'm going to draw that parallelogram and give us the area. All right. Now, a dot product comes in different flavors, but we talked about the idea of projecting one vector upon another. So when you're finding the dot product between two vectors, you're finding really the component of one vector that's acting in the direction of the other. It's just a question of what your perspective is. All right, so what we're doing is we're taking this area, this bounded area, and finding the component of it that's acting in the direction of the cross product. All right, so we have all of these, like infinitely many vectors in this span that have some component acting in the direction of the cross product. And so what that does is it creates, for every one of those vectors, it creates height. Now, if I could draw it better, this would look wonderful, but I can't. If you come away from this being like, all right, it looks like a rectangular prism of some kind, then that's the idea, all right? What it's really supposed to be is a parallelepiped, right? Which is why the technology assignments exists, because you experience what these graphs are supposed to look like as opposed to what I just constructed. Right? But what this is doing is it's taking the components of the area that's acting in the direction of the cross product and then aggregating all of those over the course of the span. Right? And when you compile them all together, just like volumes of cross sections in Calc 2, when you put all of those areas together, smush it all together, you create a volume. All right? So a triple scalar product is in fact giving you the volume of the parallelepiped that has those three vectors as its basis. All right. So the basis of the three-dimensional system, you're talking IJK. That would allow, if you create a linear combination of those three vectors, it would allow you to create a vector that would span any part of that three-dimensional system. All right. But I could never find the volume of a parallelepiped that has infinite length, right? Because it would have infinite volume, right? But if it's maxed out in a certain, at a certain length in any direction, then I can make a determination of what that volume is going to be. Now, if those vectors are along axes, that's easy, length times width times height. But if they're going off into weird directions, that makes it a lot more challenging. So this concept allows us to very easily come up with those volumes very quickly and easily. All right? So anytime they're asking you to find the volume of a parallelepiped, they're asking you to find the absolute value of the triple scalar product, which is the same as saying find the determinant and drop any negatives that might be there. All right. So number 11 and number 12 just got a whole lot easier. Although number 12 is impossible if you have no idea what the word coplanar means. Oh, sorry, this is me not telling you what coplanar means. All right, so. I am batting 1,000 now. That's an expression, if you don't know, that means that I'm just all over the freaking place. Making mistakes left and right. Blame it on the burrito I had before I came here. It was Kirkland. You know, when you get the free samples at Costco, like, everything tastes great. But so then you buy it in bulk. And then you go home and you're like, tastes a lot better in small doses. So I'm having an internal struggle right now. So anyway, we're going to find the determinant of this. Now, something to keep in mind, not that I don't think that you were necessarily overly concerned about this, but I've already assessed you on your ability to find a determinant, right? So by hand. So there aren't many circumstances in which I'm going to feel the need to do that again. And by that I mean the next time I'm going to ask you to find a determinant by hand would be the final exam. All right, so if that's something that you need to take to begin with. All right, so bottom line is this is going right in the calculator. Now, I've been chatting up a storm while typing all this stuff in, so hopefully I at least typed some of it in correctly. So I got negative 40. Now, volume's an absolute measure, so it doesn't matter what direction we're going from vector to vector, it matters what the absolute value is. So the volume here is going to be equal to 40 cubic units. All right. Now, number 12 is the one I kind of alluded to last class. It was talking about coplanar. And I said, did I screw it up?
I just did it the other method and came up with a very different answer, so I'm running my number right now.
Let me run my numbers too. I typed it. It's matrix A. What'd you get? You got what I got? Okay. Misstep. So for the next one, the coplanar term, I remember being a wise guy last class, and I said the key to understanding how to do this one was knowing what the word coplanar meant, and then I moved on. I never told you what it meant. All right, coplanar means that the points exist on the same plane. All right, so if 3 points exist on the same plane, they're coplanar. But in this case, we're talking about vectors. So it applies to the same concept, or the same concept applies. It's saying that all 3 of these vectors are living on the same plane. So if that's the case, how much volume would they contain? If they're all, basically if your length, width, and height are all on the same plane, do I have any height? relative to the other two dimensions? No. Right? So if one of the dimensions is equal to 0, then the volume should be equal to 0. So the volume should be equal to 0. So if I find the triple scalar product, or the determinant of this 3 by 3 matrix, determinant the biggest challenge here is just typing it in, of course. So I get -6. So that's wrong. So what did I type in incorrectly? 224. Because it wasn't asking me if it was coplanar. It was saying it flat out was coplanar, so it needed to give me a result of 0. So when I got something other than 0,
Too far, not too
right, I fixed it in the calculator. I was just about to do that. So we got 0. All right, now something else to keep in mind, and this is a property of determinants. So let me actually just do the operation first and then talk about it. Back. So determinant, I'm going to select matrix A. Oops. And that little T there. I put a little T after the A for some reason. And I still got a 0. What does that little T represent?
Oh, transformation.
Transpose. All right. So one of the properties of determinants is that the determinant of A is equal to the determinant of the transpose of A. Right? So we've been putting these vectors in as row vectors because that's what the rule said. But throughout the entire course, we've become accustomed to writing our vectors as column vectors because it just made more sense, and we learned a bunch of skills related to that. What I just showed you is a justification for the fact that you can put these vectors in any way you want, as long as you're consistent about it, and you're going to get the appropriate volume. All right? So whether I put 205 in as a row vector or a column vector, I'm still going to get the same determinant. All right? So it kind of it smooths things out a little bit because people get worried, oh, well, I'm going to screw that up. I'm going to put it in vertically when I'm supposed to put it in horizontally. You really can't screw it up as long as you know that you're looking for a determinant. All right, so that should be pretty helpful. Now, we'll talk about what the fourth dimension looks like next class. It's either next class or the following class. But you think about, because we talked about this earlier in the course, we're learning a lot about 2D and 3D because everything after that is very abstract, but the same processes apply, right? So we're going to learn about what a determinant in a 4 by 4 matrix is telling us geometrically, right? Which is a really weird thing to wrap your brain around because you're still talking about a volume, but a volume within the fourth dimension, right? So there's a little bit of instruction coming on, like we have to talk about what the fourth dimension looks like, right? So that's coming down the pipeline. All right, so vector spaces and subspaces. This is more proof-based stuff, still more theoretical things, but we do need this in order to really get into the application stuff. So a lot of this is a rehash of stuff that we already knew. All right, we know what a vector is. We know what a vector space is. All right, so vector space, any kind of linear combination of vectors. All right, addition, scalar multiplication. All right, and all of these properties apply. All right, so what happens is we have real space, which is really just us spanning through a real number system in 1, 2, 3, 5 dimensions, doesn't matter, just with numerical values. But what vector space does is it allows you to span through real space using vectors as your basis, right? So it's just another way of saying a linear combination, because if I'm using my vectors as the basis of that space, then I can define any movement in that space based off of its relationship to the given vectors, right? So I, J, K are our standard unit vectors for a three-dimensional system, so I redefine everything in terms of I, J, K, all right? But what if I wanted to change my basis? So instead of I being 1, 0, 0, I is 1, 2, 1. You know, what would my movements look like in that reality? That's something that we're gonna have to play around with. But for now, we're just gonna make a determination of whether or not something is considered to be a subspace of a given vector space. All right, so we have our properties. The properties I think are pretty standard, but the subspace, definition of a subspace is if the conditions are met, W is called a subspace of a real vector space V if W is a subset of the vector space V, and W is a vector space with respect to the operations in V. All right, so all more varied ways of saying linear combination, but the conditions are really where we want to kind of live, because this is how we're going to verify whether a vector represents a subspace of a given space. All right, and when we talked about span back in the first unit, we're really just talking about the idea that, okay, so sometimes a vector may not be in the span created by 2 other vectors, 3 other vectors, whatever it is. All right, so that span corresponds to the subspace. All right, if you span out to the entire real number system, then it's not a subspace, that's the vector space itself. But maybe, for example, just keep it simple, if you're dealing with just 2-dimensional system X, Y, your subspace could just be the first quadrant, all right? Because it's just a subset of the original system, all right? X going from negative infinity to infinity, and same thing for Y, all right? In order to be a subspace, the 0 vector has to be in it, all right? That's the easiest thing to test for, and it's also kind of like from a student perspective, your best friend, because if it's going to fail to be a subspace, it's probably going to fail in that step, right? And if it does, that means everything else is irrelevant, and that's good news. U and V are any vectors in W, then the sum of those 2 vectors would be also in W, all right? So it would be a closed system. We talk about, and I do enjoy the symmetry of it, in Algebra 1, in my high school Algebra 1 class, 9th graders, we talked about real number systems. But we're talking about just like integers, whole numbers, and stuff like that. But we do talk about a concept of closure, you know, having a set be closed under a given operation. So if I say that a set is closed under addition, that means that if I'm given a set of values, that I could add any 2 values and the result would be in that given set. Like, for example, whole numbers. I could add any 2 whole numbers and still get a whole number as a result, right? But the set of whole numbers is not closed under division, right? Because if I divide any 2 whole numbers, the result is not necessarily going to be a whole number. 2 divided by 3 is not a whole number, right? It's the same idea here. I'm looking for closure. I'm looking for U and V that are already vectors in W to be closed under the operation of addition, meaning their sum has to also be in the set of W, in this case, whatever that real system, vector space is. If C is any real number, so a scalar multiple, and U is any vector in W, then the scalar product has to also belong to the vector space W. All right, so those are the things we're looking for. So what does it boil down to? Proving a linear combination yet again, right? Just using different vocabulary. And so something to look forward to. Something not to be intimidated by. That's the one thing I wanted to throw in there. Not missed one. So guided example. And then I got a bunch that are not guided. So it's pretty straightforward when you're given general terms, because there's really not much to do. So I need to verify that my sum is going to be in the vector space W. My scalar product is going to be in the vector space W. But even before I do that, I want to make sure that the zero vector is going to be a possibility. All right. And so all I'd have to do is make a statement that as long as A1 and A2 are equal to 0, or can be equal to 0, I'll be fine. All right. So unfortunately, that means that you go the distance for a question like this, but that's not terrible because there isn't really much to do. All right. So if A and or A1 and or A2 can be equal to 0, then the 0 vector is accounted for. If I add these two numbers, assuming that A1 and A2 is some real number, the result will also be a real number. Scalar product, multiply C by U, it's going to be in the set of W. All right, there's no reason to think it won't be. All right. So it's pretty vague, but it kind of gets the mechanics of the concept across. And the same thing with the next one. You know, it's just expanded up to omnidirectional and, you know, dimensional. So you can go up to n by n. So, but it's basically saying the same thing. Be intimidated, something to actually look forward to. Oh, you said but on the next page, we get into one where we have to kind of do it ourselves. And this is a little bit more interesting. All right. So again, we're defining W3 as the subset of real space 3. All right. So vector space W, a vector space where W is in 3 dimensions, is part of the real number system in 3 dimensions, consisting of all vectors in the form of A squared, and B. All right. All that's telling me is the form of it. So whatever my first entry is in the vector, the second entry has to be the square of that. All right, so if this is 2, that's got to be 4, necessarily. There's no choice. If that's a -1, that's got to be a +1. Right? B could be anything, though. All right. So first thing I would want to do is verify that the 0 vector is a possibility. All right. So can the 0 vector be in W3? All right. And so the way I would do that is just very simply taking my given vector and setting it equal to 0. All right. So yes, if A is equal to 0, or B is equal to 0, or and B is equal to 0. That's the only way we have a 0 vector. All right. But it is a possibility. So let me just give you a quick what-if scenario. Let's say, you know, like I would say, what if this were, the second entry were A plus 2? Then you would start thinking, well, in order for this to be the 0 vector, A would have to be equal to 0. But if A is equal to 0, then the second entry would have to be 2, because 0 plus 2 is 2. Then it would show that there was no way that the 0 vector could be in the set. Because even if I were to, like, if this said A plus 2, and I let A equal -2, then that would force that one to be -2, just to make that one a 0. So it would all fall apart. All right. So it doesn't take much to find a scenario where it doesn't play out. In fact, I might make that an example in a second. All right. So we've satisfied the first condition, which is, you know, academically fine. As a student on a test, it's not what you're hoping for. All right. So now what I'm going to do is I'm going to find the sum of any 2 vectors in this system. All right. Well, they're vectors in the form of A squared, and B. All right. So I can make anything I want. So how about I let U equal a sub 1, a sub 1 squared, and b sub 1. And v, b, all that same stuff just with sub 2's. And so I want to know if the sum of u and v is going to be in the set, the vector space W3. All right. So I add them together, and I see. So u plus 3, u plus v. I don't even know where I came up with that 3. And I would say that this is probably the hardest part of a question like this, or relating to the concept, is that you get this and you say, all right, yes, no, did I do it? What does this tell me? Did I get the answer? Do I have an A? Well, you got to go back to what the form of W3 is. The form of W3 is any vector that has the first entry squared giving the second entry. All right? So the question would be, is this in that form? All right? So is that in the form of W3? And so I would need this entry squared to give that entry. So is A1 plus A2 squared the same as A1 squared plus A2 squared? And the answer is only if there's zeros. All right, so that's a problem, because we need it to always be the case, because these are general terms. So not always. Therefore, do we have a name for this? No, so we're going to say the vector is not a subspace of W3. So if that checked out, if we got this relationship to be true, because B1 plus B2, that we don't really care about that one, because B was a unique value, it wasn't related to anything else in the vector. But if this checked out, then we would check scalar multiples and see if that ended up giving something that made sense. We usually save the scalar multiple case for last, because that almost always checks out. So, you know, if it's going to fall apart, it's going to fall apart in this step. Right? So that's assuming you get past the zero vector concept. All right, so I'll create that side example that I was talking about. Yeah, I'll just say off on the side here, what if dot. So let's say it was in the form of A plus 2, and then I'll just keep it simple, B. All right, for this one, we wouldn't even get past the first step, all right, because what I would want to know is 0 in the set of W3. Does 0 belong to the set of W3? All right, so if that's going to be the case, then what I would do the exact same thing I did before. I would take my A plus 2, and B, and set it equal to 0. So in my first computation, well, it's not even really a computation, I get A equals 0. For the second one, I get A plus 2 equals 0, which means A is equal to negative 2. Well, A can't be two different things at the same time, so this is a contradiction. So the vector is not a subspace. Of W3. All right, so another little instance where things start to kind of fall apart. All right, but it falls apart in different capacities. It's a question of, does it fall apart because of the zero vector, because of the vector sum, or because of maybe a scalar multiple? All right, scalar multiples are kind of trickier to come up with examples off the fly, but basically anything that would lead to a contradiction in value is something that would kind of fall into that category. All right, and anything that involves maybe a transcendental function, you throw in a trig function and it tends to upset the apple cart pretty easily. All right, so oh, that writing is huge by comparison. All right, so I'll put a star on the next example for you. It's just kind of getting at the same idea, just in a slightly different way.
Trust me. Believe me.
Oh, that time it was just me. All right, good. All right, we're back. No, because I thought it was, my counter wasn't going. I thought it was having the same problem again, but it's good now. All right, so all we're looking to see is if we can create a linear combination of scalars that would make V1 and V2 give me Y. All right, so I would define C1 as a scalar multiple of V1 plus C2 V2, and that has to equal Y. So it's going right back to the first unit. And that's what this theorem allows us to do. It allows us to streamline the whole approach so that instead of testing it out case by case, if we could see that one vector is in the span created by the others, then it is in the subspace of real space. All right, so that amounts to C1, 1, 0, negative 2 plus C2, negative 2, 1, 7, giving a result of H, negative 3, negative 5. All right, which I could rewrite. Oh, that time it was just me. All right, good. All right, we're back. No, because I thought it was, oops, my counter wasn't going. I thought it was having the same problem again, but it's good now. All right, so all we're looking to see is if we can create a linear combination of scalars that would make V1 and V2 give me Y. All right, so I would define C1 as a scalar multiple of V1 plus C2 V2, giving us, and that has to equal Y. So it's going right back to the first unit. And that's what this theorem allows us to do. It allows us to streamline the whole approach so that instead of testing it out case by case, if we could see that one vector is in the span created by the others, then it is in the subspace. It's really just a question of real space.
Can I
so that amounts
find
to
the scalars by guess and
C1,
check? Can I find
1,
the linear
0,
combination by guess or check, or do I have to just do what we've always done
C2
and use row reduction techniques to get where I need to go?
7.
All right, and so, well,
Giving a
fortunately or
result of
unfortunately, depending on your
negative 3,
perspective,
negative 5.
this is a row reduction situation, but since there's an H in there, we're stuck doing this one by hand.
Right, so I'm just going to do
which I could rewrite.
2R1 plus R3. Oops. And that's going to give me a 0, 3, and then 2H minus 5. Giving us, all right, it's kind of hard to think this way, but there isn't really much you have to do because you don't have to go the distance in all cases. In most cases, because you really just want to make sure that there isn't going to be a pivot value in the last column of any row. So if I do a
it's really just a
negative
question of
3R2 plus R3,
find the scalars.
what that's
by
going to
guess
do
and
is
check.
it's going to cancel
Can
out
I
the
find
3
the linear
in
combination
the
by
middle
guess
of the
and check,
bottom
or
row.
do I have to just do what we've always done?
So I'm
and
looking at
use
1,
row
negative
reduction
2,
techniques to
H,
get where I need to go.
0,
Right,
1,
so
negative 3.
Well, fortunately or unfortunately,
And
depending
then
on your perspective,
0,
this is a row
0,
reduction situation,
so I'm
but
going to have
since there's an
9
H
plus
in
a
there,
2H minus
we're
5,
stuck doing
so
this one by
2H
hand.
minus
so I'm
4.
just going to do a
2H plus 1
4.
plus R3.
All right. And so, in order for a solution to exist, this guy
That's
here
gonna give me a
cannot
0.
be equal 0.
3, and then 2H minus 5.
All right. In order for that H negative 3, negative 5 to exist, that has to be anything other than 0.
All right. It's
Right.
kind of hard to think this
Oh, I'm sorry.
way, but
There isn't really much you have
my
to do
head
because you don't
is
have to go
in
the
space right
distance.
in
It
all
must
cases.
equal
in most
0.
cases,
Because you really just want to make sure that there isn't going to be a pivot value in the last column of any row. It absolutely
So,
has to be
if I do
equal
a
to 0.
negative
No exceptions
3
whatsoever.
R2 plus
no,
R3.
because if it's anything other than 0,
What that's
then
gonna
that
do
makes
is
the
it's gonna
pivot in
cancel
last
out the
column,
3
which causes there to be no
in
solution.
the middle of the
All right,
bottom
so that
row.
must equal 0, and that's going to define for us
So
what
I'm
H
looking
has to
at
be in order for
1,
the solution
negative
to
2
exist.
H,
So 2H
0,
plus 4
1,
equals
negative
0.
3,
Therefore, H equals negative
and
2.
then 0, 0. So I'm going to have 9 plus a 2H minus 5, so 2H
All right,
minus
so
4.
that's just telling us, because again, it's saying
2H
for
plus
what values
4.
of H will Y be in the subspace of
And so,
R3 spanned by
in
V1
order
and V2?
for a solution
So
to exist,
really, it's just, again, getting at
this
the idea
guy here
that
cannot
a subspace
be
and
equal
a span
0.
are really talking about the same thing. Right. It's just, if you're spanning any
Right.
segment
In order
of
for
the real, of
that
real space,
H negative 3,
that
negative 5
may or
to
may not be a
exist,
subspace.
that has to be
Right? Because if you're
anything
capturing all
other
of the
than
real space,
0.
then it's not a subspace by definition.
Right.
That's all of real space. Right?
Oh, I'm
So
sorry.
I'm telling you, keep it simple.
My head is
If you're
in
dealing
space
with
right
just
now.
a number line,
Must equal
and
0.
I'm telling you that there's a set going from negative infinity to infinity. If somebody were to
absolutely
say
has
that
to be
that's a subset of
equal
real
to
numbers,
0.
That wouldn't make
No
any sense.
exceptions whatsoever.
Right? Because
Yeah, no,
the real
because
number
if it's
system
anything
goes from
other than
negative
0,
to infinity.
then that makes the pivot
So
in the
that's
last
not a
column,
subset,
which
that's
causes
the
there
set.
to be no solution.
Right?
All right,
Now,
so
if
that
I
must
tell you
equal 0,
that
and that's going
I
to
have
define
the
for us
number
what
from
H has to be in
infinity
order for the
infinity, I'm only
solution to
going from
exist.
0 to infinity.
So
That
2H
is
plus
now a
4 equals
subset.
0.
All right. So what
Therefore,
I'm looking
H
for
equals
here
negative 2.
is something that is not the entirety of a real space, just a subspace, a subset of that real space.
All right, so that's just
So
telling us,
when you
because
add
again,
line,
it's saying for what values of H
most often
will Y be
have
in
the same
the
definition
subspace
as
of
subspace,
R3 spanned by
except in
V1 and
those
V2.
instances
So
where you
really,
have,
it's just,
for
again,
example,
getting at the idea
IJ and
that
K,
a
which form
subspace
the
and a
basis of
span are
real
really
space
talking about the
dimension
same
3.
thing.
Yeah,
Right.
they'll
It's just,
span out
if you're
the
spanning
entirety of real space.
any
In which
segment
case, it
of
would be
the
a
real
subspace,
of real
it would be the
space.
space itself.
That's
Right.
that may
So,
or may not be a subset.
Now, if it turned out that
Because if you're
I,
capturing all of the real space, then
2i,
it's not a subspace by definition.
and K,
That's all of real space.
then I'm
Right,
losing
so if
one
I'm
entire
telling you,
dimension now.
keep it
That
simple.
would be a subspace.
If you're dealing with just a number line, one key factor.
And
that
I'm
forms the
telling
basis
you
of
that
real
there's a
space.
set
All right,
going
so
from negative
a lot of
infinity to
lot
infinity.
of weird
If
terminology,
somebody were to
but
say that that's a
ultimately,
subset of
in
real
most
numbers, that
cases,
wouldn't make
it's
any
just
sense.
telling us that what we
Right,
already know
because
is something
the
that
real
could be
number
applied
system goes from
to
negative
just
infinity.
with different language.
So that's not a subset, that's the set. All right. Now, if I tell you that out of the numbers from negative infinity to infinity, I'm only going from 0 to infinity, that is now a subset. All right. So what I'm looking for here is something that is not the entirety of a real space, just a subspace, a subset of that real space. All right. So with that in mind, span most often will have the same definition as subspace, except in those instances where you have, for example, I, J, and K, which form the basis of real space dimension 3. Yeah, they'll span out the entirety of real space, in which case that wouldn't be a subspace, it would be the space itself. All right. So now if it turned out that you had I, 2I, and K, then I'm losing one entire dimension. Now that would be a subspace because it's not going to incorporate one key factor that forms the basis of real space. All right, so a lot of weird terminology, but ultimately, in most cases, it's just telling us that what we already know is something that could be applied to just with different language. All right, so null space, column space, dimensions, right? All right, so these are characteristics of subspaces. So more terminology and things like that. Some of these things the calculator does, and some of it we just have to do by hand. Some of it is related to things that the calculator does that we just kind of have to interpret things that we already know how to do in the calculator just in a different way. Right. So the null space of an n by n matrix, written as null A. Right. Linear algebra notation can be weird. It's like, what kind of abbreviation is that? What?
Is that a typo bonus?
No, I mean,
Yeah.
That's real.
yeah, that's actually what the notation is, but like, it's not like we're going down from logarithm to log. We're going down from null with 2 L's to null with 1 L. Like, come on, man. I know why. It's because they made column space col, and they want it to be consistent with the number of characters, but it's just, I mean, at some point you just gotta kind of move away from being so particular about structure that, whatever.
Span is 4.
Yeah, I know. I think the only thing I could come up with is that they didn't want it to end in a vowel either. Because if you had spa and then spa A, yeah, they really could have done anything. Like anything other than what they chose to do.
Oh, potato.
Yeah, the potato A. Ah, yes, that's true. Then we'd have that conversation. It's pronounced potato. Yeah, so it's a set of solutions of the homogeneous equation AX equals 0. So it's like, wait, what? The null space of an n by n matrix A written in this form is the set of all solutions of the homogeneous equation AX equals 0. All right, so if you're rightfully thinking, wait, we've done this already. You're with me. Yeah, we have done this already. We're just giving it a different name, and we're going to use it for something else. All right. So in our set notation, we write null A, and then x such that x is in Rn, whatever that space is, and A of x equals A times x equals 0. So basically, what this is getting at is the variable and the condition related to the variable. So what is x equal to? Right. So all you're doing is representing your parametric form of your linear system AX equals 0 matrix equation. All right. So our theorem. This is why it's important. Null space of an M by N matrix A is a subspace of real space N. Also, the set of the solutions to this system AX equals 0 of a homogeneous linear system in N unknowns is a subspace of Rn.
All right, so what this is telling us is that it is guaranteed that the solutions to a homogeneous system will be a subspace of the real number system. All right, so it's taking something that we already know and kind of merging it with something we're just learning about. Now, column space is a set of all linear combinations of the columns of A, all right? Also talking about the span. Now, when we talk about the column space of a matrix, what we're talking about is the relevant columns or the minimum number of columns necessary to create a span for whatever the system is that you're dealing with, all right? Because let's say, for example, you have a 4x7 matrix, all right? So 4 rows, 7 columns. All I need are if I have 4 rows, all I need are 4 columns in order to span out 4 space, all right? So that's telling me that I'm gonna have 3 extra columns that are unnecessary, right? They're just extraneous. So it's just really asking me, well, which are the ones that I really need, right? And which ones can I get rid of, right? That's what the column space is talking about. And this is really, the theorem is just really kind of getting across that idea. The dimension, right? So the dimension of a vector space is the number of vectors in the basis for V, all right? So that's going back to column space. So the number of vectors that form a basis for your vector space, right? So again, if I have a 4x7 matrix, I only need 4 of those columns. Those 4 vectors make up the basis of 4 space. So it's a question of what those vectors are. Well, I know what my dimension would be because I would have a need for 4 vectors, so my dimensions is going to involve a 4, but those 4 vectors form the basis for 4 space, all right? If I had a 5x9 matrix, I would need 5 columns in order to get that same job done. All right? We've been kind of living in the world of 2x2s and 3x3s, and so what we're trying to do is kind of get across the idea that everything we know about 2s and 3s can be expanded to higher order dimensions. And it's just a question of really just taking the necessary components and working with it. So dimensions of null space A and column space A. Dimensions of null A is the number of free variables in the equation, and the dimensions of column A is the number of pivot columns in A. All right, so I think that would make sense because when you're talking about a pivot column, you're talking about the variable that you're solving for when you actually rewrite your solution in parametric form. Okay, so I would have maybe a pivot if I had 4 variables. If I had a pivot in 3 of the columns, that's telling me that one of the columns is going to be associated with a free variable. Right? So now I indirectly know what my null space is going to be related to in terms of free variables and the number of columns. So the sum of those 2 values should actually give you the total number of columns in the matrix. All right, so really, I mean, again, the dimensions of null in column A, column space of A. Dimensions of null A is the number of free variables in the equation. Dimensions of column space A is the number of pivot columns in A. All right, so really, you know. So we talked about the null space, the column space, the definition of dimensions, and all that stuff, the null, col, and all that good stuff. I really talked on this whole page without writing anything down. That's interesting. What can you do? It's all the same. We've been doing this the whole time. It's just we're talking about it in a different capacity. All right. So we have A and U, and they're asking us to determine if U belongs to the null space of A. All right. So again, null space is a solution to the homogeneous system. I would need to make a determination of whether or not that falls into that solution. So let's solve the homogeneous system. So AX equals 0.
so with my R ref, I'm getting this good looking solution. All right, so I could write this, I mean, there's an implied x here, even though I wrote ax equals 0, I didn't show the step of defining my vector x equals x1, 2, and 3. So you're kind of hand waving around it, but this is really the same as saying x1 minus x3 equals 0. x2 plus x3 equals 0. And then we have the free variable x3 equals x3. So we're looking at x1, 2, and 3. Everything's going to be a multiple of x3. So add the x3 in the first equation, I'm going to get a coefficient of 1. Subtract it in the second equation, I'm going to get a coefficient of -1. And it already has a coefficient of 1. In the last one. All right. And so now at this point it should just kind of pop off the screen at you where we're asked to determine if U belongs to the null space of A. Right? So this is the solution to the homogeneous system. Any scalar multiple of the vector, the base vector 1, -1, 1, because 1, -1, 1 forms the basis of the solution. Any scalar multiple of that is going to be representative of that null space. All right. So now I don't have any other values here, so I don't have to really worry about linear accommodations coming into play, in a more expansive context. Like if I had like 4 or 5 different free variables, it could be kind of tough to figure out if U falls in a set, but U actually is what this would be if x3 is equal to 1. So we could say that U is in the null space of A when x3 is equal to 1. All right. Not always going to be that easy, but never going to be that hard. Once you come up with your solution, most of the time it's just a matter of saying, oh, that's 10 times what U is equal to, or 1/3 of what U is equal to. You'll see what the scalar is, and it's pretty easy to just kind of pop that off. All right. All right, so for the next one, we got to do a couple of things. We got to find the column space, and then we also have to find the null space of A. But really, it's just going to boil down to the same process, because we need pivots. All right. So if I wanted to, I could go back into the first example and identify the relevant columns that form the basis of this system. All right, because I had 2 pivots. The first column and the second column had the pivot entries in it. So my first 2 columns of the matrix would actually form my column space. Right? So that's actually pretty easy. So if I wanted to, they didn't ask me to, but I could actually kind of off on the side here say that the column space of A would be the set containing the vector 2, -3, -5, and the vector 6, 2, -4. And again, the only thing I needed to do in order to figure that out was identify where my pivots were and what columns those corresponded to. All right.
So those pivots correspond to the first and second column in the given matrix. So I have it. So what does that tell me? Well, rhetorical question. It tells me that I don't have to do anything different in order to find the column space, right? Because it's going to come out in the solution for finding the null space, all right? So I'm really just, in both cases, when I'm looking for a column or null space, I'm using the process I would use in order to find the column space, the null space, and then just kind of pulling out the column space from there, all right? Unfortunately, because we're spoiled now, it means that we got to type a new matrix into our calculators. But if we always keep in mind that the alternative is to do all this crap out by hand, it'll help you sleep at night, I guess. All right, it's a homogeneous system. Just doing a quick double check of Ruski here. And there it is. Just do a little copy paste. All right, so there's my RF. We're looking for that's funny. I entertain myself sometimes. I just had this moment where I was like, crap, I screwed this problem up because I saw the what is K, and I'm like, there's no K in there, what did I do? And then I realized I forgot my own question. It's a subspace of R, K. You're like, what dimension am I working with, right? So the column space, again, represents the basis of the system. So it'll tell us how many vectors we need to define our system. So what I'll do first is I'll identify the column space using a marker. So the column space of A is going to be the original vectors associated with the pivots. So I got a pivot right, meow, meow, and meow. So 3 meows. And so that's going to correspond with the one right, meow, meow, and meow. All right. Again, I need a marker, not a highlighter. So I write the original vectors, not the row reduced form. All right, so I needed 3 vectors to span this real space, all right? So the column space is a subspace of some real space. I needed 3 vectors. That means that I must be working in 3 dimensions, all right? So therefore, K is equal to 3, giving us real space in the 3rd dimension. All right. Now, generally, the number of rows will dictate the column space, or the number of vectors that make up your column space. The problem with that, relying on that relationship, is some of the sneakier questions that you can kind of see when you're dealing with row reduction. Like, what if one row is just a scalar multiple of another? It's not a unique equation in your system, right? So it didn't even need to be there to begin with. So you could have like a 5 by 5 matrix,
but maybe there's only 2 unique equations in there because 3 of them are just repeats of the other 2, the 2 base equations. So we got to be careful about that, which is why we do the row reduction technique to begin with, right? So now the null space involves us coming up with a solution of the system, right? Again, we're solving AX equals 0. It's very easy to just hit R ref and write down some numbers. You always want to keep in mind what the point of it all is, right? So x1, so I have 4 variables that I'm working with here. So x1, 2, 3, and 4 is what I'm up against. So x1 is going to be equal to negative 9x3. x2 is equal to 5x3. And x4 is equal to 0. All right, and so we know that x3 has to be the free. So x1, 2, 3, 4, I'll just write x. Is going to be x3, and we're looking at negative 9 for x1, 5 for x2, 1 for x3 because x3 is equal to x3, and 0 for x4. All right, and so that is my null space. And that's probably the best way to do it. So this is null space today. All right, now I just want to highlight something for you. We are indirectly finding these values all along. So if I wanted to find the dimensions of the null space, really it's just, well, how many free variables did I have? 1, right? Number of pivot columns, how many vectors made up my column space, all right? So in this case, I could say that the dimensions of my null space would be 1 and 3 respectively. All right, the reason I bring that up, well, aside from just teaching it, is because I was about to put a star on number 3, and I realized I hadn't talked to you about how to find the dimensions yet. I mean, I talked to you about the definition, I didn't talk to you about how to actually apply the definition. All right, so then we're on page 76. So it's saying find the dimensions of the null and column space for A. All right, so we know to find the column space, we just need to identify the pivots. So that's what we'll do. Now, sometimes, I mean, you get in the habit of see the matrix, type the matrix. You know, you see it, you take the calculator out, you turn it on, and you start typing stuff in. There was a reason why we talked about earlier in the course identifying whether a matrix was in reduced row echelon form. And so this is really one of those moments. Reduced row echelon form is the ideal state of a matrix, but any echelon form will help you identify what the pivot values are, right? And so again, the pivot values are the first non-zero values in any row, and also they need to be to the right of the pivot value that's in the row that precedes it, right? So in my second row, my first non-zero value is right here. It is certainly to the right of the first non-zero value in the first row. That's also true in the third row and in the fourth row. All right. Now this is not a linear system of equations, so the fact that there's a pivot in the last column, that doesn't mean that there's no solution because these are just a set of vectors. All right. This is not an augmented matrix. This is just a coefficient matrix. We haven't set it equal to anything. All right. But
just looking at this, I can easily identify the columns that have the pivots in them. All right, so these are my pivot columns. That is not a marker. All right, and there's 4 of them. All right, so the dimensions, or the dimension of the column space of A is going to be equal to 4. All right, there's 4 columns that make up the basis of this system. All right, now the 4 rows that make up this matrix they're kind of giving you a clue that that's what we should have been on the lookout for to begin with, because if I have 4 rows that make up a matrix, then odds are I'm working in 4 space. If I'm working in 4 space, if I'm going to span out using 4 vectors, or using any number of vectors, but if I'm going to span out all of 4 space, I would need 4 vectors to do that. All right, those would form the basis of my 4 space. All right, so it makes sense, but sometimes you could have one row that's just a scalar multiple of another. So like the unnecessary rows that make up the matrix. All right, so that's telling me that if I were to solve this, if I were to find the solution to the homogeneous system by setting it equal to 0, multiplying it by some vector x, setting it equal to 0 and solving, I would get a certain number of independent variables and a certain number of dependent variables. All right, so the ones that are dependent would be related to the null space. So what that means from our perspective is just whatever is not making up the basis of the column space is going to be our null space. So the dimensions of the null space of A is going to be 3. All right, so we didn't really have to highlight them or identify them in any capacity. We have 7 columns. 4 of them are related to the dimensions of the column space. The remaining 3 have to be the null space. All right, it's always number of columns minus the dimensions of the column space. That will give you the dimensions of the null space. And we're also going to talk about what that means geometrically. So, as we go forward, you're going to see like these words actually mean things, like null. Usually null and void. Like to cancel something out, the emptiness, something along those lines. Like an empty set, a null set. How does that tie together with this? That's what we're going to learn about. All right, so row space and column space, and rank, row rank and column rank. It's all pretty straightforward stuff. It's just procedural. So we've already covered this. It's just a question of like the vocabulary. Row equivalence. This is kind of weird. This is a matrix B is row equivalent to matrix A. It's just like awkward, but I can't think of any. I'll take it as a typo though. Maybe any matrix B. Yeah, I'll write it that way. Because it kind of looks at first glance like it's somehow supposed to be matrix A, but it's not. So I'll say any matrix B is row equivalent to matrix A if B results from A via elementary row operations. All right, so that's something we knew about from way back when. That's what row equivalence is talking about. It's a scalar multiple or any other elementary row operations, then we're defining that as row equivalence. Right? And that's really getting at the idea of those extraneous equations that make up a matrix. Right? So if you're looking at a row equivalent, a matrix that's row equivalent to another one, then it doesn't necessarily have to be there. All right? So if A and B are 2M
by n row equivalent matrices, then the row spaces of A and B are equal. All right. So what we want to do is find the bases, right, of row and column spaces. All right. So this is it's process. So it's not bad. And the first step in the process is something you're very familiar with, reduced row echelon form. So row reduction. All right. The non-zero rows of matrix A in reduced form give. Oh, okay. So forgot to put matrix A, but I guess it doesn't matter. Non-zero rows of the matrix in row reduced form give the basis of row space, the row space of A. The non-zero rows. All right. The columns containing the pivots, those give the basis of the column space of A. All right. Now we've been learning about column space really all along because we've been defining our matrices as being, the columns of those matrices as being the vectors related to, whatever space we're working in. But the reason why we talk about row space in addition to column space is because basically when we're talking about the cross product, we can represent a matrix using the rows as the vectors as opposed to the columns. All right, so we can say vector 1, 3, 2 as a row of a matrix as opposed to the column, and if that's the case, then certain rows would form the basis of that system as opposed to the columns. All right. So what we want to do is we actually want to know what the row and column rank are. All right. The dimensions of the row space of A is called the row rank, and the dimensions of the column space is called the column rank. All right. The row rank and column rank of the M by N matrix A are equal. All right. Since the row rank and the column rank of M by N matrix A are equal, we only refer to the rank of A, and we use this notation. All right. It's important to understand what a rank is talking about, but again, I mentioned this throughout the entire course. The vocabulary is what's going to get you, because we're talking about the same thing over and over again, but just using different terminology. The rank is just talking about the relevant number of vectors necessary to define the basis of a system. All right, so if I'm in 3 dimensions, the rank of my matrix better be 3 if I'm saying that the vectors that make up this matrix define the basis of that system. Because if they don't, then what am I doing? What's the point? All right, so we want the rank to be consistent with the number of dimensions that we're working with. So if we're in the 4th dimensions, I want the rank of the matrix to be 4. Right? But the good news about this is that all I really have to do is figure out the dimensions of either the row space or the column space, and I'll have the rank of the matrix. All right. So then we have this statement here. I'll take it as a typo. I think I didn't tab it over the right way. I think I put it in as a table. If I just shift this over a little bit, then the then would fit there, and it would look a lot nicer. So for this typo, I would say just submit bottom of page 77 reformat. All right. I start to get the idea as as we progress through the course, that when I talk about the typos, like a good percentage of the class has no idea what the hell I'm talking about, because I keep saying these typos and then nobody ever submits them, and then the corrections don't ever get made. You've submitted, but you're maxed out.
That was the question.
Yeah.
You get 3 right.
Once you get your 3, you're done. So, like in the early part of the semester, I get a lot, and then all of a sudden, it kind of fades out from there because people get their max. But I don't have a lot of people maxed out in this class, right? So odds are, and especially this is a pretty dense course, that like there are other classes that you're probably taking that if you had an opportunity like this to submit typos, you whip out the phone and you submit it right away, and you wouldn't miss anything. Here you kind of miss an entire concept if you do that. So, but I can tell you that if you submit the typo, like even when you get home, if you submit the typo, just make a note, submit it when you get home. odds are you're going to be one of the first people to submit it. And then you'll get the bonus, and then, once you get your 3 points, you're done. You don't have to worry about it anymore. But you could still continue to submit because, every class, I point out like 3 or 4 of them, right? So 16 weeks, twice a week, 32 classes-ish, I'll bring it down to 30. Let's say 4 times per, that's 120 typos. And those are the ones that I recognize. It's the ones that I don't recognize, those are the ones I'm worried about. Because, this is a true story. I only learned like 2 years ago that IT' does not mean that something belongs to it. Like, its shoes. Like, I thought that like, if I wanted to say, like, Billy, no, that doesn't make sense. The dog and its bone. No. Apparently it means it is. What the hell? I've been living my whole life that way. And commas, I'm a fly by the seat of my pants user of a comma. Like, this is really how it goes. I'm typing, and then I'll be like, yep, feels like a comma moment. Put that bad boy in there and move on. Right? Or my other train of thought is, haven't used a comma in a while. Feel like I'm due. Put one of those in there and hope it doesn't underline it in some weird color.
I'm convinced that the comma usage has changed in the last 15 years. Because in English class here, she completely rerouted my entire way of thinking about commas. I'm like, this is not how I was taught the first time around.
I just thought it was like,
they changed their mind. Something happened.
maybe, yeah, that makes sense because, like, I feel like somebody along the way told me that, like, when you're reading something, if you stop to take like a full breath, that's a period. If you stop and take like a half a heartbeat, that's a comma. And then just kind of guess for a semicolon.
Eventually it was, right?
Yeah. I knew it was like 2 complete sentences that you, for some reason, want to put together. But then I always thought to myself, well, why can't I just make 2 complete sentences and just do it that way?
Yep.
I've never seen a semicolon that I've been like, yeah, absolutely.
Yeah, that seems like a perfect usage of a
I thought of it as like when you can place a because or and statement or something like that.
Oh.
Or place like that, but it wouldn't sound weird. I could place
Kind
a
of like a
semicolon.
therefore.
Yeah.
Yeah, I might just use that. I think that works because there have been times where I've been like, I got a 50-page packet here. I didn't use a single semicolon. All right, let me just jack 2 sentences together and put a semicolon in there. And then people will be like, that's not how you use it. I'm like, well, sue me. I don't know. I don't even know semicolon. So, but yeah. Colons I think I'm pretty strong with. So, the dimension of the column space, which is also the same as the dimension of the row space, we call that the rank of the matrix. It's always going to be easier, I think, to identify the column space and therefore the dimensions related to the column. So column space, and so therefore the rank should come from that. Row space, I mean, you got to actually solve a homogeneous system in order to do that. For a column space, all you have to do is row reduce and find your pivots, all right? So it's a lot easier in that regard. The nullity, now I'm just making up words. The nullity is the dimension space, or the dimension of the null space, all right? So if you know what the general dimensions are for, or the overall dimensions are for the matrix, once you identify the rank, then you have the null space because they have to add together to give you n, all right? So n is the number of columns. If you have 7 columns and only 3 of them are pivots, then your nullity has to be 4, right? Because it's got to be the remaining ones. Because all 4 of those would be related to free variables in some capacity, all right? So the nullity of A, again, is the dimension of the null space. What people have struggled with in the past, aside from just generally having to know lots and lots of words,
is the column space seems to have a counterpart that would naturally be row space. You think columns, rows, column space, row space, but then all of a sudden it's column space, null space. And it's like, okay, you just threw a curveball at me. Like, why is this going on? Why is this happening? But I've always thought of the row space as just what I would do if I represented my matrix as having, instead of columns representing vectors, the rows are vectors. Like, I'm just changing my perspective. So very rarely am I looking for the row space, right? Because generally I'm representing the columns of my matrix as the vectors of that matrix. I keep saying it, a lot of interesting stuff coming. And you know what, I may never pay that off by saying the interesting stuff has arrived for fear that you might not find it interesting. If that's the case, I can't handle that kind of pressure. So I'll just let the interesting things happen, and then I'll read the room. And then after the interesting things happen, if I feel like you also found it interesting, I'll say something like, wasn't that interesting? I've been talking about these interesting moments all along. But if I look around the room and I see people are like, that was horrible, that was not a payoff at all, then I'm just gonna let the moment pass and not even gonna bring it. I won't even bring it up. All right. This is just all right. So I'll just go back to this. Somebody got the typo for this, which I was appreciative of. That I was able to clean that up in my notes. But the rank of the matrix is the dimension of the column space. The nullity is the dimension of the null space. So that's what we were working with. All right. So we're in good shape. Find the basis of the column spaces that find the basis for the vector space. Right. So it's just adding more words to it, seemingly to. All right. So find the bases. It sounds weird when I say bases, I know, but I really emphasize that because when I say bases, people for whatever reason have no idea what the hell I'm talking about. But when I say bases, they're like, ooh, wait a minute. That sounds a little bit like basis. All right, so it's the plural of basis. All right, so if I have the basis of a system, the bases would be, like, am I talking about 1 vector, 2 vectors, or 10 vectors? Give them all to me. All right, so I want to find the vectors that make up the basis of this matrix, also known as bases, and the rank of the row and column spaces for A, given that matrix. So it's basically just taking everything that we've been covering and putting it all together. So with that in mind, you get a nice juicy star for each one of those bad boys. And then I encourage you to read through the important results on the bottom and study them. Oh, look at that. That's a typo for somebody. This is from the old textbook. That shouldn't be there. I missed one. All right, and so that's pretty much where we're going to leave it for tonight. Next class, we'll talk about, just kind of putting a ribbon on this, the idea of bases, and we're going to get into the concept of change of basis. All right, so it's kind of altered reality. So it's when things are going to start going from bland, dull memorization to a little bit more interesting. So we just had to kind of plow through this stuff. Determine the bases, rank, and nullity. Make it as complicated as possible, but I promise you that's not the point of it. All right. Of course, you have to take my word for that at this point. So, there's a number 1 also? It's not, that's my problem. I go to a page, it's automatically bringing me to the last thing I was on, and I'm just never seeing the one that came before it. All right, so, so we gotta row reduce this bad boy. Again, this is how we know we're spoiled. Because you're like, dang, I gotta type all that stuff in. Back in my day.
Don't you wish you could just take a picture with a calculator?
That would be so great.
Like how you can scan credit cards and that?
Yeah.
To type it in.
That's gotta be something. Because I know they have like that, you know, like those apps that you cheat on your homework with. Like you take the picture of it and it solves the problem for you. Like, but for like a noble cause, you know, not like cheating on your homework, like for actually just simplifying things. I mean, the closest I ever got to that was back in the day when we used to use like real textbooks. Some of those textbooks came with CDs that had all the data sets in them. And so for the calculator, you'd have to connect your calculator to a computer and then put the disk in, and then you could transfer all the data sets to your calculator as needed. So it was like, you don't have to type in all this data, you could just transfer it over. But you needed the disk, the wire, and some sort of third-party software to actually do the transferring. So it was like, okay, nobody can do that, so what's the point? So that was really the closest we got to that. I think I typed it incorrectly. I'm just gonna go with it. So, gonna RF this bad boy. 4x5 matrix. Who do you think you are? All right, well, that's something. So, get my pivots. Whoop, whoop. And one more whoop. Right, yeah. All right, so these are my pivot columns. Oh, keep doing that. That's a habit I gotta break. Pivot columns. So the column space of A is going to be the first, second, and fourth columns. So these form the basis of this real space. Scooch that over. All right, so the dimensions of the column space of A, the dimension is 3, so that makes the rank of matrix A equal to 3. All right, so these are the same. They're the same thing. Somewhere along the line, somebody decided, you know what, writing dimension of column space of A, that's just way too much work. So we'll just call that the rank. I mean, I guess rank is a good enough word as any, because really it's just telling us what the relevant vectors are in the matrix in order to define the real space. Right, so yeah, I mean, I guess it's fine. I mean, if you wanted to compare one matrix to another, you talk about the rank. Well, this one has, I mean, it can define real space with 3 vectors, and some other matrix has to use 4 vectors to do it. Another matrix has to use 2 vectors or 5 vectors. It gives you a sense of the hierarchy of things. But at this point, beyond that, it really doesn't tell us much of anything. Now, the column space is also defining the basis of this, whatever this system is, of this real space. So this is these are our bases. All right. Now this one didn't say it, although I think it's a good enough question to include, just for consistency between 1 and 2, that I'm gonna throw it in. So I'll take it as a typo. Dimensions of the null space of A. Well, we had 5 columns. 3 of them were related to the rank. So the remaining 2 of them have to be related to the null space. All right, so that means the nullity of A is equal to 2. All right, because again, these 2 things are the same.
Always.
Always. All right, so it's just basically giving a new name for the thing that we've been working with. Again, for the same reason why they decided to call this the rank, they decided to call that the nullity. I mean, the one thing I could say about this is at least it has null in it. But if they took such great pains to abbreviate null space of A with an NUL, look at the inconsistency here. They went the other way and they're like, oh, let's just call it nullity. For number 2, I forget where I got this problem from, but I've always been kind of curious about the need to include the fact that n equals 5. I mean, it's pretty clear that n equals 5. Because again, it's m by n matrix. M is the number of rows. N is the number of columns. I don't think that statement needs to be there, even though I've had it there for years.
Maybe so we gotta assume the last 2 columns don't exist because they're just
Yeah,
zeros.
I guess. Yeah, I guess we could leave it in. I don't know. I'm sure I'll regret taking it out the minute I take it out, so. But it's already in reduced echelon form. So, I mean, we have our pivots. So those are pretty clear. Continue with my red here. So I don't actually even have to put anything in my calculator. So the bases I hate when I do that. I underestimated my need for a bracket. There's 5, right? Yeah. All right. The rank, again, is the number of vectors that make up your basis or bases. So your rank of A is equal to 3. It's glitching again. And then the nullity, again, is whatever's left over. So the number of columns that do not make up the rank. I'm going to try to fix this again. This looks ugly.
I think the n equals 5 clarifies that we should look at them as nullity.
Yeah. Yeah, and that
I guess it's helpful for a confused student.
yeah, okay. We'll go with that.
A little cheat thing.
Yeah, because I guess somebody could look at it and say, well, that's just the 0 vector twice. Do they even need to be there? Yeah, okay. That's probably what the rationale is behind it. So that's what we're going to go with. Okay, so we have our 3 bases. Now, the 0 vector is never going to form the basis of any real system because it's not spanning out in and of itself. It's where a vector is pinned. So it's necessary in that it has to be part of a system, but it's not going to be a basis of a system. Right? So, like, how are you going to define a linear combination with a vector, with a zero vector? Like, oh, I can multiply it by 2, and how am I going to get another vector from that? I'm still going to end up at the zero vector. Right? So, all of this important result stuff, I mentioned that this is going to be important, so hence the title. Let A be an n by n matrix, so a square matrix. A is non-singular, meaning it's invertible if and only if the rank of A is equal to n. All right. So you have an invertible matrix only if and only if the rank of that matrix is equal to n. So n here is 5. The rank is 3. This is not going to be an invertible matrix. All right. So this is one of those things I teased it a couple weeks ago, where we were talking about inverses, and it had that big old list of the different properties of inverses, and one of which talked about the rank. And I said, well, we haven't learned about rank yet, so we can't really talk about this just yet. And so, if that's the case, you know, like, you're really considering like that moment in time as like, well, this rank business, what is that going to be all about? Now you flash forward and you think to yourself, maybe, whoa, that could have been really useful to know way back when. The problem is you would have had to learn all of this stuff in order to understand what rank is. And so it really wasn't an appropriate time to talk about it. But now, just looking back on that, if we're talking about determining if a matrix is invertible, all I have to do is find the rank of it. All right, so put it in reduced echelon form. If it's already in reduced echelon form, even better. Determine that matrix's rank, and if it's not equal to n, then it's not invertible. All right. So rank of A is equal to n. All right. So still working off of that. A is non-singular, which is what I just talked about. The determinant of A has to not be equal to 0, and you will have a unique solution. All right. If the rank is less than n, then and A is non-singular, then A only will have the non-trivial solution. Well, I'm sorry, will have a non-trivial solution. And then the final one, let A be an m by n matrix, so now it's not a square matrix anymore. Then Ax equals B has a solution if, there's a missing if, the rank of A is the same as the rank of the augmented matrix. All right, so you can make a determination of whether a matrix has a solution, a matrix equation, Ax equals B, has a solution just by looking at the rank of the given coefficient matrix and the rank of your augmented matrix. All right, so it really kind of saves you a lot of time and energy. But, you know, your students thinking about a test. Think about the last test. Those true-false questions, they're really right here. You know, it's just a question of, like, can you take this information and use it to create a counterexample? All right, so I'm gonna look out for. All right, the linearly independent sets and bases. It's all pretty straightforward stuff. Definition of basis, we really kind of beat that to death. But I'll just say that it's really relying on linear independence. So there has to be a linearly independent relationship. Now, if you remember back to I think it was the first unit, it's telling us that the only way that you have linear independence is if, when you solve the homogeneous equation, you get the trivial solution. All right? So I'll make a note of that. So the homogeneous is Ax equals B, so solve Ax equals 0 and only get the trivial solution. All right. because the other part we just went over, showing that V1, V2, all the way to VK spans V. Right? So that's just determining span. That's really nothing. And all of these examples are really just kind of getting at that idea. Right? That's how we know something forms a basis of a real space. All right? So you can look over these examples, but they're not overly challenging. But I wanted to go through one with you. All right? So what I'm going to do, because it's asking if it's a basis of real space 3, it's not asking us to determine if some value is in the span of that set of vectors. So what I could do, I mean, it would be a royal pain, and we did it like this back in the last unit or 2 units ago, is we defined some arbitrary vector we called ABC, and then we solved it to see if that vector still existed when we performed elementary row operations. That was brutal. But now if we know that linear independence is a key ingredient, then what I could do is solve the matrix equation AX equals 0 and I'm only looking for the trivial case. All right, so, and again, unless there's some crazy variables involved, there's no reason why you would need to do this by hand. All right, so three by 4.
I think it's 2010.
2010.
The second.
What did I screw up?
The second one.
So I got 111, 201, 120. Right, that's good. So I screwed it up in the calculator?
Yeah.
I don't. If I did, I'm not seeing it.
No, that's
I'm good? All right, thanks, man. So, reduced row echelon form of matrix A. And so, shockingly, I got the trivial solution. So through RF. All right, so what that means, okay, so the interpretation here is incredibly important because this is really how we start to understand what a basis is talking about, right? What we just showed is that vectors 1, 2, and 3 are linearly independent of one another. And what that means is that, well, aside from the obvious thing, they are not dependent on one another. It means that I'm not going to be able to get from one vector to another using simple scalars, right? So I'm not going to be able to write, for example, 102 as a linear combination of vectors, like vector 1, you know? So if I were to say something like 2 times vector 1, or 3 times vector 1, or negative 1/2 times vector 1, I'm not going to be able to get vector 2, right? So through simple scalars, I'm not going to be able to get from one vector to another, right? So they're linearly independent of one another, which means that they're functioning kind of on their own path, right? Since I'm working in 3 space, what it's giving me is a recipe to define any vector in 3 space using linear combinations of these 3 vectors, all right? So since V1, 2, and 3 are linearly independent, they form a basis for real space dimension 3. And that's specifically, again, because there's 3 vectors. All right, my penmanship took a dive here, so I'm going to just fix it real quick. They form a basis for real space 3. So if it turned out that one was dependent on the other, that's kind of like when you have one row that's just a scalar multiple of another row. In a matrix, you're saying, well, why did that row have to be there to begin with? It didn't really contribute anything. That's the same idea here. Like if I had another vector like 2, 4, 2, well, that's just double 1, 2, 1. That's not going to form a basis because it is already based on another vector. All right, so if these 3 vectors are in no way based on each other, then they form a basis of something else. That something else being all the other vectors that exist in real space 3. All right, so yeah, I think that's probably good enough. You know, one more thing. So, the important result, I don't want to leave off before addressing this. If S represents a basis for vector space V, then every vector in V could be written in a unique way as a linear combination of the vectors in S. Right? So that's what I was addressing here. So if I'm saying, for example, that I wanted to write a vector like 10, 17, 32, there is some linear combination of these 3 vectors that can get me to that desired vector. All right, but what we're going to need to do is come up with a basis decomposition of certain vectors. Now, that's actually pretty easy if you know what the bases are, or bases are. So, looking at number 2, it doesn't look like we have enough information to do it. Basis decomposition is the same thing as saying write it as a linear combination of its basis vectors. All right, so I'm going to write 3, 4 as a linear combination of its bases. All right, so you got to think about what the bases are for a 2-dimensional system. All right. It'd be what? 310. 310. Exactamundo. So we're looking at 310 plus 401, and that's because 1001 form the basis of real space dimension 2. All right. So the basis decomposition of 1, -1, 4 would be the same thing. Now, some people, prefer to go to the IJK notation because 1, 0 is I, 0, 1 is J. In 3 dimensions, it's 1, 0, 0, 0, 1, 0, and so on. But this, I think, tells a better story. So here we'd be saying 1, 1, 0, 0 plus -1, 0, 1, 0 plus 4, 0, 0, 1. And again, we're talking about bases. All right. So the important result there is that we have S that represents a subset of vectors, non-zero vectors in vector space. W represents the span of those vectors. Then subset of S is a basis of W. All right. So if we know that W spans out all of vector space, and S is defined as that particular vector space, then S forms the basis of W. All right, so the process for finding a basis, you form a linear combination, homogeneous, set it equal to 0, construct the augmented matrix associated with that equation. The vectors corresponding with the columns containing the leading ones form a basis. And so that's what we were talking about. We were kind of building towards this. It's just telling us find the pivots, but then go back to the original matrix and identify what those vectors were corresponding with those pivots, and that'll give you the actual basis for that vector space. All right. So in this case here, it's really not difficult because I already kind of geared you towards it. So you have your bases. And this is consistent with real space dimension 3. All right, so that's the subset of this set of values S that form the basis. And you can look at 230 and 132, and just like we were talking about on the previous page, you can write 230 as a linear combination of these three vectors. You can do the same thing with 132. All right, but you can't write 001 as a linear combination of 100 and 010. All right, the individual bases are they're ones that they have to be standalone. They can't be represented as linear combinations of other bases. All right, so that's the key ingredient. And so